Why is the double-slit experiment so mind-bending? Imagine watching light or tiny particles like electrons pass through to tiny slits and seeing a pattern that looks like ripples on a pond. That's what makes this experiment so fascinating. It's like a puzzle that challenges what we think about reality. When particles go through the two slits, they don't just behave like tiny balls. Instead, they act like waves, creating bright and dark bands on a screen behind the slits. This pattern is called an interference pattern, and it's a signature of wave behavior. But here's the twist. If you try to watch which slit a particle goes through, the interference pattern disappears. The particles suddenly act like tiny balls again. This shows that observing them changes how they behave. It's as if the act of measurement itself influences the outcome. This dual-wave particle nature is a core idea in quantum mechanics, the branch of science that explains how matter and energy behave at very small scales. The experiment was first done by Thomas Young in 1801 to prove light behaves as a wave. Back then, many believed light was made of tiny particles, but Young's pattern of bright and dark fringes proved otherwise. It was a big shift in science, showing that light can act like a wave. Later, scientists extended the experiment to electrons and other tiny particles. They found that electrons, which are particles of matter, also create interference patterns when passing through the slits one at a time. This was shocking because it meant matter itself has a wave-like nature. When scientists measured which slit the electron went through, the pattern vanished. It was clear that the act of measuring disturbed the system. This idea is called quantum superposition, where particles can exist in multiple states at once until observed. Physicists like Albert Einstein and Niels Bohr debated about what this meant. Bohr explained that measuring the particle's path disturbs its wave nature, destroying the interference pattern. This is tied to the uncertainty principle, which says you can't know both the position and momentum of a tiny particle at the same time. More recent experiments use even more precise tools, like individual atoms, to test these ideas. They show that the more we try to find out about a particle's path, the less clear its wave behavior becomes. This experiment is not just a science curiosity. It's helped develop new technologies like quantum computers and secure communication systems. It shows that at very small scales, reality doesn't follow the rules we see in everyday life. Instead, particles can be waves, and their behavior depends on whether we look at them or not. The double-slit experiment is a key milestone because it reveals how strange and wonderful the quantum world really is. It challenges our ideas about matter and energy, and it reminds us that observation itself shapes what we see.